All right, next we have 4 more spotlight presentations. The first one is Bilevel Learning of the Group Lasso Structure, presented by Jordan Frekan? No?
Thank you very much. Hello everyone. So today we present this bilevel approach to estimate the group lasso structure. So we consider the case where we like to predict a vector y from some matrix X. And to do so, we could look for a linear model where we need to find a vector W such as y equal x times W. However, in many cases, only some part of X might be relevant to predict y. So this is why you should prefer a solution W, which is group sparse. And one efficient way to do so is to resort to the group lasso problem. So given some parameter lambda and the prior knowledge of the group structure, the group lasso solution minimizes the sum of two terms. The first one measures the discrepancy between y and x times W, and the second one enforces group sparsity. Here you see an example where W hat is made of 5 groups, and only the first and the fourth group are relevant. So there exist many efficient solvers to find W. However, it requires the group structure to be known in advance. And in this work, we propose to estimate the optimal group structure. So to do so, we consider a multitask setting, where we have T group lasso problems sharing the same group structure. The groups are encoded by a binary matrix θ1 to θl, and each column of θ encapsulates different groups. For example, the first group is made of the first 18 features, so θ1 is equal to 1 from 1 to 18, and 0 otherwise. On the left side, you can see different regressors. And here, for example, the fourth task only used the first and the fourth groups. So now we have recast the problem of learning the groups as the problem of learning this binary matrix θ. And to learn θ, we propose a bilevel approach. The lower level problem is made of the T group lasso problems, and the upper level problems permit to select θ according to some criterion. For example, you could choose the validation error. So U of θ will measure how well your solution generalized to new data. However, there are two main difficulties. First, W hat is not available in closed form, and also it is not a smooth function of θ. So in order to overcome these two issues, we propose an approximate bilevel problem. This problem is very similar to the one before. The only change is that we have replaced W hat by WK, which is the output of a dual algorithm that converges to W hat. And this dual algorithm involves two mappings A and B as follows. First, the dual variable U is updated k times using the mapping A. And then WK is obtained by using the primal dual relationship B. So now the goals are twofold. We would like to find mappings A and B that are smooth in order to smooth the upper level objective UK. And also, we like to prove that this approximate bilevel scheme converges to the exact one. So here are the contributions of our paper. First, we have proposed this bilevel scheme to estimate the group lasso structure. And also, we have designed a dual forward-backward algorithm with Bregman distances chosen to make A and B smooth. And also, we have proved that by using this scheme, you can have the convergence of your approximate problem to the exact one in terms of minimum value and in terms of minimizer. So now that UK is a smooth function of θ, we can minimize it by using, for example, the Prox-Saga algorithm, which is a variant of the projected gradient descent. So let's now take a look at some results. Here we would like to estimate θ star that I've shown in the previous slides. And to do so, we let our algorithm estimate and group the features into at most 10 groups. On the left side, you can see the recovered solution. It has currently identified the first 5 groups, and currently identified the next 5 ones as being empty. And on the right side, you can see the impact of this approximate parameter k on the validation error. You can see that for small values of k, you have performance as badly as Lasso, and if you increase k, you reach performance close to the group Lasso with the oracle groups. For more details, you're welcome to our Person 92. Thank you very much.